Hey everybody, welcome back to another video of solving LeetCode challenges. We have a very interesting problem today. We are gonna see a solution for problem 1268, search suggestion system. So imagine you have an e-commerce website, or you are a company that you have a list of products selling on your website. And you want to suggest the user as soon as the user start typing, you want to suggest them some products in your whole repository, search them quickly, and then suggest them based on what users have typed. So probably you have seen that on Amazon, for example, when you start typing mousepad, for example, let's say you're looking for a mousepad, and as soon as you add a new character, so as you can see, it is updating the suggestion system list of 10 suggestions as soon as you put the next character and update your search. So for mousepad, so starting from this product that matches to other products that have starting with mousepad but still suggesting them. So it is very similar problem. Here, for example, we are given a list of products. Let's say we have these products, and for every character that user type, we should return a list of maximum or up to 3 words that matches in our repository based on what user have typed. So for example, the first one is the result of the output after user type M. The second row is after user type MO, and then MOU, and etc. until we don't find anything. And the other criteria is that if there are more than 3 products, we should only return the 3 products that sorted lexicographically in the whole repository. So the quickest way to solve this when it comes to mind is that one way is we can iterate through all products and then just filter them based on all words starting with M, for example, and then sort them and then return the maximum 3. But the question is, can we do it in a more performant way? And the answer is yes. So imagine a tree. We know that in the problem it says that all products and search keywords and everything are only consist of lower English letters. So we know that there are 26 English letters from A to Z. And then imagine a tree format. So starting from a root, each root has 26 children. And then the first children is a similar node of all words starting with A. And the second children stores all words starting with B, and etc. And recursively, this first node, the first children, also has 26 adult children. And the first one stores all words starting with AA. The second one in all words starting with AB, and etc. So in this way, whenever users start typing, so we can quickly filter all words starting with M by just O1 by reaching to the children, the M children in that node. Without necessarily finding to see or visiting other products, since we might have up to 3,000 products, or in Amazon, for example, it could be millions of products. So we don't want to iterate through all of them. So let's first start working on ignore the problem and then design our data structure. So as we discussed, we have a node. So let's define a class node. And then what does this node have? So let's init function for that. So each node might have 26 children, but initially all of them are none. And as soon as we add the new words into our repository, we want to update them. But initially, self children equals none times 26. Initially, each node has 26 non-pointers. Because all repository only consists of lowercase English letters. Also, each node might have a value or might store a word, which is also initially none. So for example, when we add them, each node has 26 children, and also a value or a word itself. That is, so if in this case, for example, a mouse, when we traverse through the tree from mouse, and then at that node, we should also store mouse itself, that we have a word or keyword matches to our in our repository. And as it is also mentioned in the problem, all strings in the products are unique. So if we didn't have that, we should also have another counter or something, or a list of words to store them. But we know if there is any word, at maximum it is only one, and then we store them here. And then the rest of the children is for example, mousepad. So mouse itself, we can store it here. And then mousepad or anything start with mouse but has some other suffixes goes through the children. So we should also implement a recursive add function, that we add a new word into our repository. And for each word, we should keep track of the word itself and also a path that we are iteratively going through the path and then find them. So initially, for example, a mouse, the path is mouse, and then at root node, we find the children that for all words starting with M, and then subtract the first letter, and then this is the path. But we keep track of the initial word, so that whenever this path is empty, so in the second round, we find the children that start with O, and then U, S, E, and then finally, when the path is empty, we just add the word as a value or the word for that specific node. So if length of path is less than 1, that means it is over. So we traverse the tree properly, and then we should add it to the current state. So the word called word, and then return. That's it. But otherwise, the index, so we should map each English letter into 26. So for that, I want to define a helper function, def index, for a character, which return the order of this character minus the order of A. So in this way, we can map A to Z to 0 to 26. So int equal index of paths, the first character, and then if self the children of that index is none, so because we initially just defined all nons, so this is now we should initialize that first. Self the children is a new node. We initialize it here. Otherwise, if it is already initialized in the previous iterations, we just call the add function recursively to add a word. But now we removed one character from the path. So what we return is the path, anything after 1. So we remove the first character from the path and then leave it to the child node to add that. And that's it. So this is our add function. So let's store all products into our data structure first. So we have a root, which is a type node, and then for each word in words or products, root.add word. And what is the path? So for each word, the path is also the same. So for mobile, for example, the path is mobile, but mobile doesn't change as a word, but the path changes. So at each iteration, we remove one character from mobile until the string is empty, and then we add it to our repository. So this is our add. At the end, whenever we are looking for something, we should also return a list of words, or we should define a collect function or suggest function for a node. So whenever we are at a node, let's say we somehow traverse the tree, and then we know that we want to suggest anything at the current node or below, up to 3 words, because our suggestion system should be designed such that return at maximum of 3 words, also sorted lexicographically. So anything that starts with A should come first, and then B, and then C, and etc. up to Z, but in a maximum of 3. And we know the root value itself is the smallest among all of these words, and then anything in the A children, and then anything in B. So for that, we know that it is of maximum of 3, but what I want to do is to total. I define a total. By default, here is 3. But let's say in the future, we want to change our data structure so that it returns a maximum of 5 words. So we know without changing the code, so we can update that or call the function with other parameters to suggest the words. So it is sort of, this is our budget, and then we are at a node, and we should collect maximum of total words and recursively go through the children and then collect them. So let's say answer or suggestions equal an empty list first. If self.word is not none, that means the root itself has a value, or there is a word already in the current node in our repository. So suggestions that append self.word. So we should also keep track of the number of words that we are adding to our suggestion so that we never go beyond total. So it is cnt equals 0, and then we add cnt plus equal 1. And then for each children, for I in range 26, now we are going iteratively through the children and then from A to Z, so that we make sure that if we collect anything from A, we are adding them to our suggestion first, and we don't have to be worried about the lexicographically sorted criteria that the suggestion should be sorted. So in this way, we make sure that they are already sorted. So if self.children, that our children is not none, then we call the same function, suggest. So self.children, that specific children, that suggest. But what is the total number? Now, our budget is total minus CNT, because we have already, we might have used 1 already, and we don't want it to return 3 characters. So our budget at the current state for this children is total minus CNT. And we should also check if total is less than 1. If the budget is over, we simply just return an empty list so that we don't suggest anything because we have no budget left. So suggestion from children. This is some words that the children is suggested. And then we should, so we add them to our suggestion at the current node, plus equal this new list, and then cnt plus equal the length of this new children. This is we could keep track of the number of words that we are adding to our current suggestion. And this is it. And if somehow cnt, after some point that we're collecting children from the collecting or suggesting adding suggestion from the children node, if at some point CFT is less than greater than total or equal, we can break that, so we don't have to iterate until up to Z and then remove them. So we can break now and return. This is the all words that we have found in our suggestion system, and what we should return up to total. So if it doesn't have any, that's fine, but the maximum of total, which initially is 3 words in our suggestion system. So now we have implemented the add function. We iterated through all words and add them into our repository. And we also have a suggest function, so that whenever we call it on a node, then it goes through itself and then all children in order from A to Z, and then find a maximum of total words and then return them. So for example, here, if I say root.suggest, so at root, that means there is no character added, nothing is typed yet. But for the output of this problem, what is needed is that we should traverse the tree first, so the keyword, we iterate through all characters in the search word. So the first one is M. So we first find the M children. So ignore A to Z. We call the suggest function on this node, and what it returns is that it is collecting anything start with an M up to 3 words. And then the second character is O. So we go to O, and then this is the second node that we also should call suggest function on, and then U, S, E, and then up to the end of search word, and then return them as a list of all suggestions. So this is the suggestions for letter M. These are suggestions for MO. These are MOU, and etc. So this is what we should iterate through or traverse through the tree using this path or search word. So this is our list of nodes that we wanna call suggest function on. Initially it is empty, and initially our node is root that we wanna see the traverse. So for each letter or for each character in search word, we say new node equals the node the children, and the index function that we implemented here that maps anything from A to Z to 0 to 26. So the index on that letter. This is the current node, and then node that append the new node. But sometimes we might not have anything because initially we initialize all children to none. So we say if node is not none, do that. Otherwise, we might have some bunch of nones in our list. So for example, in this repository, as you can see, all of these words are start with M. If the search word is apple, for example, our node list or the nodes that we see here would be none, and then that's it. So all of them would be none. And then at the end, we have a list of nodes. So the output could be node.suggest, and by default it is you should find 3 words for each node in the list of nodes. But what happens if this is none? So we first check that if node is not none, else it is an empty list. So if a node is none, we know that there is no word in that current state, and then we just instead of calling the suggestion, because the node itself is none and it doesn't have any suggest function, so we just return an empty list. But otherwise, we call suggest function on that node. So in this way, on the traverse for a keyword, for example, mouse, we found some nodes. We traverse, collect them, and store them in this node list. And then on each of them, we are calling suggest function. And then storing all of the answers that we find from these suggestion calls into this list at the end. So let's debug that. Let's run what we didn't write. So invalid syntax, len path. Oh, I forgot an if here. Let's see other errors. Okay, so the length of that, the CNT is an integer that we want to we store the values, but the thing CNT is supposed to call the length of anything that we collect from the children. Okay, it seems to be we don't have any other errors, so let's just clean up the code a little bit, and then remove extra spaces. Let's submit that. Okay, so that was everything. As you can see, it is a large problem, but we used trees for our suggestion system. If you want to see further, I would put the code in the description as well. But this is what most people suggest for this problem, and it is actually what is happening in e-commerce and websites like Amazon. When you start typing, This is how they retrieve the products from their data structure or repository. That was everything for this video. Hope you enjoyed it.